Now, in this lecture, we shall be discussing about the practical example of a golf club and considering that it has to accommodate more than 300 people. So, if it is accommodating more than 300 people, then definitely, we are looking forward to a situation where we have to, we can say, adjust the annual probability of exceedance, or we can say the importance level. So we shall come on to this also, but before that, we can just, assume that the structure that we are considering is as same as what we have done in the earlier example. And this is, let us suppose it is a golf club, and the floor heights are basically 3.5 meter each. And the whatever forces are coming, that has to be distributed like vertically as per the AS 1170 part 4 requirements. So all the loadings that we have discussed in the earlier lecture, that is kept same, so that we can compare both the results. So in here G1 1750 and the and live load reduction factor is 0.6. So 1000 plus 0.6 into 750, that gives us 1450. Similarly, 2000 plus 0.6 times 750 gives us 2450. The same equation here, and the same shall be written here also. That is 1250 plus 0.6 into 500 gives us 1550 kilonewton. So total seismic weight is 7900 kilonewton, the same that we have discussed in the earlier example. Let us say location of the structure is Dampier, and importance level, as it is occupying more than 300 people, it is considered as importance level 2. So as per that importance level, from table 3.1, that is building code of Australia, the annual probability of exceedance has to be taken as 1 by 1000. After that, probability factor KP, that also is like dependent on the importance level itself, and that is 1.3. And hazard factor, that too depends upon the location, that is Dampier. So for that, Z is equal to 1.2. So KP into Z, that is 1.3 into 0.12. That gives us 0.156. And let us assume that the soil that we are discussing is shallow soil. So for shallow soil, the soil site subsoil class as per the code is C, and earthquake design category is basically 2. So we have already discussed that how you can calculate the earthquake design category as per the height and the type of soil and the values of KP and Z. So this is the table 2.1. And if you refer to this and the inputs that we do need to check, we do know that importance level is basically 2. So we are right now sitting around here, and the site subsoil class. So site subsoil class, that needs to be taken as C. So we have to refer to this particular, and this is the range where we do need to check. So KP into Z value is basically 0.156. Sorry, so this needs to be referred. That is the value is greater than 0.12, and height of the structure, that is less than 25 or greater than 20. It is less than 25. So that is why we have to consider the earthquake design category as 2. So if this is an earthquake design category 2, then we can proceed forward with static analysis also. So structure form factor for reinforced concrete moment frame, that is KT is 0.075. Natural period of structure, that can be calculated as 1.25 times KT and HN to the power 0.75. So that gives us 0.679, and natural period exponent, that is basically 0.679 divided by 2, and we do need to add 0.75 to that. So that gives us 1.09. So as per this particular value, that is 0.679, we can calculate the value of CHT from the table 6.4 or from the graph also. So CH value is into T times comes out to be 1.84, and structural ductility factor is mu is equal to 0.4, and performance factor is 0.67 as per the RCC fully ductile moment resisting frame. So horizontal C is equivalent static shear force acting at the base, that comes out to be KPZ, that is 0.156, multiplied with CHT, that is 1.84, multiplied with SP, that is 0.67, divided with mu, that is 4, and multiplied with 7900. So this value comes out to be 380.3 kilonewton. After that, if you're talking about the vertical distribution of the horizontal loads, so that value comes out to be divided as 0.067, 0.239, 0.372, and 0.322. So as per these coefficients, we just need to multiply it with the total value that we have calculated here, that is 380. So 380 is like divided in 25, 91, 141 and 125. So we when we add all of these numbers, we do get this 380.3 kilonewton. So we can say that 380.3 kilonewton is divided into basically multiple levels: 25.3, 91, 141.5, and 122.5. So that is like the basic example with which we can understand how we can calculate the horizontal equivalent static shear force acting at the base, and how we can vertically distribute the horizontal loads as per the code requirements.